Thanks for the warm introduction. I am from Melbourne, and I can assure you that I probably did bring the weather this morning. Apologies for that. It's an absolute pleasure to be here and really connect with the Queensland community. Today, what I'd like to do is tell you about some of the work that we're doing in Melbourne in partnership with some of our Queensland partners here, and I'll talk specifically about a program we've been funded by the Queensland Government, which is exploiting quantum sensors for the life sciences. So the theme of today's presentation and the thing that I'm really excited about is to connect with this community, discuss the future of these quantum technologies and how it can really change our lives and our understanding of the world around us. So as Mark said, this is the International Year of Quantum, and this is an exciting year as a quantum physicist. For us, it means that we get out and about and raise public awareness about the wonderful research and innovation that's happening here in Australia. And this event represents a really good opportunity to do that, and also to engage stronger between the academic sectors and industry and government. So it's a pleasure to be attending events like this throughout the year. In terms of quantum technologies and their potential impact, as Mark mentioned, Kathy Foley has been instrumental in really pushing forward the agenda of quantum technologies. And this started, the nexus of this started back in around 2019 when Kathy organised the community to come together to really talk about the potential impacts of quantum technology. And that led to this technology roadmap which CSIRO put together, which articulated the economic and societal impacts of quantum technologies into the future. This report has been updated, so the numbers look even better than this at the moment. But this report really spurred on interest from government, and Kathy was again instrumental in developing the next national quantum strategy through her position in the federal government. And so if you're interested, we put two case studies into that national quantum strategy, which talk about the possible opportunities in quantum-based medical testing, and also new transformative technologies for GPS-denied navigation, which we can talk about a little bit later today. That national quantum strategy, as Mark talked about, is being rolled out now, and that also spurred on the development of Army's got their own quantum technology roadmap here in Queensland. It was great to see the Queensland government put out their own quantum technology roadmap. Yes, in Victoria, we're working on the same thing. I'm hopeful that can come out later this year. And also quantum technology is a big part of the AUKUS Pillar 2 Act. So there's a lot of groundswell support and government investment now in this key area moving forward. Now, for those not familiar with quantum, there are typically three segments to do with quantum technologies. There's quantum computing, quantum communication, and quantum sensing. And so looking at the panels for later today, you're going to hear a lot about quantum computing and quantum communication. So today I'm going to focus on quantum sensing, which is something that's close to my heart. So when we talk about quantum sensors, what are they? If we break it down into a simple statement. So basically quantum sensors utilise quantum mechanical behaviour in materials and exploit that behaviour to demonstrate advantage. And for quantum sensing, that advantage can come in a number of different ways. So you could create a more accurate sensor, a more stable sensor, a more precise sensor, a higher resolution sensor. So it depends on the application as to where a quantum advantage can come in. And these advantages are being applied across a range of different sectors. We're doing a lot of work in the biotechnology space as part of this ARC Quantum Biotechnology Centre of Excellence. There's a lot of work going on understanding molecular spectroscopy, the dynamics of how molecules work. There's a lot of defence work going on in terms of more precise sensors for communication and navigation applications. And also, from what you heard yesterday, there's a lot of work going on in environmental monitoring, automotive industry, geosurveying, and of course, fundamental science really underpins a lot of these technologies and the emergence of these particular applications. And I'm pleased to say that now this is leading to the creation of startups here in Australia. So here I've tried to collate some of the quantum sensing startups that have emerged following the success story of the LAN-10 project from CSIRO back in the 1990s. So CSIRO were the first to develop the squid-based magnetometer system, which was mentioned before, and that's been used to do a whole range of mineral surveys around Australia, and was the first real success story as a quantum sensor being commercialised. 20 years later, we're now starting to see a whole range of different sensors developed to meet a whole range of different applications. And so there's gravity-based sensors, there's magnetometers, there's precision diagnostics, and excitingly for us in Melbourne, we're now starting to see the creation of material foundries. So Quantum Brilliance is setting up a quantum diamond foundry in Melbourne to really feed that technology innovation, particularly around diamond. So for full disclosure, I'm involved in 3 of these startups. I'm involved in Phaser Quantum, Phoebe Technologies, and Chromos. So if you've got any interest about what they're about, please come and see me after the presentation. Today, what I want to do is highlight a particular use case, which is around Phoebe Technologies, and we'll talk more about that as we go. So the other thing I wanted to point out was in the National Quantum Strategy, they did a fantastic job of collating all of the different technologies, materials, and programs that are being done right around Australia. And as you can see, every state is participating in quantum technology in some way. And as Mark mentioned, this is really on the back of the federal government support of the ARC Centre of Excellence schemes. So we've had 25 years plus of continuous funding, whether it be through quantum computing or quantum sensing based activities. And I'm pleased to be part of the new ARC Quantum Centre of Excellence in Quantum Biotechnology, this QBIC initiative that Mark was talking about before. This has been the real game changer in providing the critical mass that we have here in Australia and the real excellence and innovation that we see. And as part of this new QBIC Centre of Excellence, the main mission for us is to utilise developments in quantum sensing and quantum imaging together with quantum computing to understand how the dynamics of single molecules, how do molecules move, how do they behave, how does that behaviour dictate emergence phenomena within cells, and how does that emergence phenomena within cells lead to complex behaviour like thought processes in the brain. So we're developing technologies that help understand these basic principles. And if we can do that, that will create impact across a range of different sectors from sustainability to diagnostics, medtech and pharma. So that's the real mission of this ARC Centre of Excellence. And today I'll tell you about one of those projects which is related to this molecules theme, so understanding the behaviour of molecules and single proteins, around the mission that we have to understand how iron is loaded into a really important protein in our body, which is referred to as ferritin. And I'll tell you more about what ferritin is. So ferritin is the iron storage protein in our body. It's a very small protein, so it's around 12 nanometers in diameter. So we're talking about a single protein is smaller than a Zika virus, it's smaller than a single bacteria. Now within one of these single ferritin proteins, it can be completely empty or it can hold up to 3,000 iron atoms in it. So it's our iron storage protein within our body. And iron is incredibly important within our bodies. It's heavily regulated. If we have too much iron, we become iron deficient, and iron deficiency affects nearly a third of the world's population. And iron deficiency can be treated, so you can take iron supplements. But if you progress to iron deficiency anemia, that's a much longer road back to recovery. So it's something we want to avoid. On the other hand, if you have too much iron, you're at risk of being iron overloaded, and you can have a condition called hemochromatosis. And so hemochromatosis affects 1 in 200 people of Northern European descent, and it's the most common genetic disorder. So the body does this really fine balance of trying to have just the right amount of iron. We don't want too little and we don't want too much of iron. And the World Health Organization has given us cut-offs that we stick to, that doctors adhere to when they provide advice around whether you're iron deficient or at risk of being iron overloaded. And so these cut-offs are for the amount of ferritin that's present in your blood sample, which is the most common way that we assess your iron status. And you can see here that for iron deficiency, If you've got less than 15 nanograms of ferritin per mil of blood, then you're at risk of being iron deficient. Okay, and in Australia, it's around 30, actually. It's a little bit higher than the WHO's recommendations. And the WHO have said that ferritin is the best biomarker we have to evaluate our iron status. The challenge is that ferritin, this protein, this spherical ball, it can either be completely empty or, as I said before, it can be completely full and hold up to 3,000 iron atoms in it. And so the way that we do the assessment at the moment is with these cheap and indirect blood tests. So when you go to the doctor and you get a blood test to evaluate your iron levels, typically they will look for the concentration of this ferritin protein in your blood. If that concentration goes below 30 nanograms per mil, then they'll say that you're at risk of being iron deficient. The problem is that's only measuring the concentration of the protein. It doesn't measure at all whether that protein is full or completely empty. And so there's a good correlation between the concentration of the protein and the iron that it holds in healthy people. But if you've got any underlying chronic condition, if you've got an infection, a whole range of different things, your body can become inflamed. And when you become inflamed, the response is to make more ferritin. And often that ferritin is empty. So this works well for healthy people, not so great if you've got any kind of disease state. There are alternatives. So you can have a very accurate but invasive procedure. So you can get a bone marrow biopsy if you so wish. I wouldn't recommend that, and that's rarely used. And there are other direct methods, such as an MRI. So you can get an MRI scan. It looks at the total iron content in your liver. And this is the most common technique for diagnosing iron overload, this hemochromatosis. The MRI is not sensitive enough to tell you whether you're iron deficient. And so there's a gap there that we need to fill. So what we'd like to be able to do is somehow take these cheap and inaccurate tests, which is a simple blood test, which is indirectly detecting the iron, and turn that into a direct iron detection method. Now, the iron that's present in those ferritin proteins is magnetic. And so we think that quantum sensors are in a unique place to directly measure the iron that's present in that protein, not just the concentration. And so there have been a whole range of other methods that have demonstrated you can measure the magnetic properties of this ferritin protein. So as I said, MRI has been used, squid magnetometers has also been used, and more recently there's been magnetic force microscopy and optical nanotweezers that can look at a single protein and can tell you about whether it's loaded or not, which is fantastic. Like, that's an amazing technology. But if you want to build a clinical assay, these complicated methods that take a long time and are very expensive won't cut it. So in Australia, we do over 10 million iron tests a year. Okay, and that number scales by a factor of 10 in the US. So if you're going to develop a new clinical assay, that assay needs to be highly sensitive, it needs to be cheap, fast, easy to operate, and reproducible. So they're the key metrics that if we are to develop a quantum solution to this problem, we have to keep those things in mind. And that leads me on to the quantum sensors that we use. So as Rob mentioned in the introduction, so our interest is using defect sensors that come in diamond materials. So these are relatively simple defects. If you take 2 carbon atoms out of a diamond, you replace one of them with a nitrogen atom, you leave the other side vacant, you create a nitrogen vacancy defect. And this defect has been studied around the world for the past 20 to 30 years. So more recently, we've worked out ways to how do we exploit the quantum properties of these defects. And one of the nice things about these defects is that those quantum properties are retained at room temperature, which is where we need them to be for a lot of these biological applications. So we can manipulate their quantum states at room temperature. And the other nice thing about this defect is we can tune it to be sensitive to a whole range of different things. So we could detect magnetic fields, we could detect voltage, we could detect temperature, depending on how we interrogate this particular sensor. So it's a very versatile platform to play with. And so staying with the theme that a lot of the quantum technology innovation has happened here in Australia. So Lloyd Hollenberg and Jared Cole back in 2009 came up with this theoretical proposal that you could use quantum systems, and in particular the decoherence of quantum systems, to measure fluctuating magnetic fields. And you could do that very sensitively. And the ion that's present in this ferritin protein is a fluctuating magnetic field. It's like imagine a bar magnet that's constantly flipping back and forward. So it creates a magnetic noise, if you like. And so this theoretical proposal suggested we could measure that magnetic noise if we had a quantum system and we looked at the decoherence or the relaxation rates from that quantum system. So it's only taken us 15 years to catch up to that theoretical idea, but we're now in a position where we can actually start to measure these things on the test case that they actually looked at in the paper, which was ferritin proteins. Now, this is my main sort of technical slide, so I'm not going to get into too much of the detail, but it's a relatively simple technique to probe these defects and these quantum properties. So with these defects incorporated into a diamond, all we do is we shine green light onto those defects. And the green light polarizes all of the electronic spins into that ms=0 state at the bottom there. And that's a really unique thing on its own. So just to shine green light onto a system and polarize all of the electron spins into one state, that's very hard to do. Often quantum technologies, you need to go to very cold temperatures or very high magnetic fields to achieve that. With this diamond defect, we get that for free and we just shine green light on it, which is nice and cheap. Then what we do is we wait and see how long does that spin stay in that state for. Okay, what will happen once you polarize it into that state, it will then interact with all of the things around it and all of the magnetic noise that it feels, and then it will relax back to a mixed state again. And that has a characteristic time associated with it. And we can read that out by simply waiting a particular time, and then we shine the green light on again, and then we look at the fluorescence, and we've got this the light that we get back from this defect depends on the spin state. So we can actually determine which spin state it's in based on the fluorescence intensity that we get back. What we're left with is one of these curves. This is a spin relaxation curve. So this tells us the average time that it takes to relax in that diamond lattice. And so the principle here is that if we were to measure ferritin, so if we were to put these ferritin proteins very close to our quantum sensors, if those proteins are empty, they contain no magnetic information. And the spin lattice relaxation time that we would measure would be exactly the same. So we wouldn't measure any signal from that ion, from the absence of the ion. As the ferritin protein loads, as we get more ion incorporated into that ferritin, that creates magnetic noise. And that magnetic noise will cause our relaxation to happen faster. And those curves get shorter and shorter. So this is exactly what happens in an MRI machine. And it's the way you generate contrast in an MRI machine. Here we're doing it on these nanoscale diamond sensors. And so we published this paper a couple of years ago now, which showed that the readout that we measure, this change in relaxation rate, scales with ion load of those ferritin proteins. So this shows you that based on the magnetic signal that you get back, you can infer the ion load of these proteins, which is a really important thing. And this was one of the first times that the ion load at these low end of the spectrum was obtained. And that was obtained due to the sensitivity that we have from these sensors. And so for those at the back, I apologise, but the ones at the front can see these little balls. This is an SEM, or a helium ion image, I should say, of ferritin that's been dropped onto our diamond sensor. So each one of these little tiny balls is one of those 12 nanometer diameter proteins on our sensor. And what we're able to show, if we look at the sensitivity of our first generation device, is that we're on the cusp of this ion overload. So we're on the cusp of being physiologically relevant for the concentrations that are present within your blood. Since then, we've got an order of magnitude better, and we want to push that again to get into this iron deficiency regime. If we can get into there, then we can start to help. As I said, you've got a third of the world's population that are suffering with one of these iron disorders. So based on those results, that's led to the creation of this spin-out company, Phoebe Technologies. So Phoebe being ferritin-bound iron. So that's the thing that we're trying to detect. And our mission here is to develop a clinical assay for this ferritin-bound iron. And that clinical assay will lead to a dramatic improvement in our assessment of these whole range of iron disorders. And I wanted to finish with a particular highlight. So this is a project that we're just starting here in Queensland. This is together with partners from Griffith University. We're also partnering with Queensland Academy of Sport, the Royal Brisbane Women's Hospital, and Queensland Pathology and ACU to begin to, I can tell you exactly the phases of the project. So the first phase is we want to continue the advancement of this sensing technology, get into this regime where we're sensitive for iron deficiency. We're recruiting samples at the moment from Queensland female athletes. So iron deficiency is disproportionately affects women, and in particular, female athletes suffer a lot with iron deficiency. And if female athletes go from being iron deficient to iron deficiency anemia, that can really impact performance. And so for the 2032 Olympic Games, we want all of these athletes to be at their peak performance. So the idea here is that we can create a test that can actually evaluate when they're at risk of becoming iron deficiency anemia. They take a supplement and their recovery is much quicker. If we can demonstrate that through the clinical trial, then we want to explore the expansion and adoption of this quantum technology to the broader community. So with that, I'll leave it there. If you've got any questions, please come and see me afterwards. I want to acknowledge the wonderful work that our group in Melbourne is doing. I want to thank the Queensland Government and all of the partners that are in the room for their collaborations and support as well. So thanks very much.